Okay, so isotonic regression in general dimensions. This is joint work with three excellent collaborators. Roy Hun from the University of Washington, a PhD student of John Wellner's. Tengyao Wong is my fantastic former PhD student and postdoc. And Sabyasachi Chatterjee, who was at Chicago for most of this project and has just moved to University of Illinois. Okay, so isotonic regression, isotonic you can think of as a synonym for monotonic. So if that was the first word that was confusing you. This is perhaps the simplest and most widely studied form of shape-constrained estimation. To set the scene, shape-constrained estimation is a field that's been around in statistics for 60 plus years now, but it's undergone a real renaissance over the last 10 and especially over the last 5 years. So people like to look at problems like estimating regression functions or density functions in a non-parametric way, but under qualitative shape restrictions. So this would be a sort of contrast to more typical methods and analyses that are based on smoothness assumptions. And the particular attraction of working with shape constraints is that often you can end up with procedures that don't require the choice of any tuning parameters. That's very unusual within non-parametric statistics, and I think gives you sort of canonical ways of estimating functions and a whole lot of very interesting theoretical problems, as well as ones that I think have significant practical applications. But in the simplest version of this isotonic regression problem, we're simply trying to estimate a monotone regression function from noisy observations at an ordered set of design points. So this project is not really motivated by one particular application area, but I think it's not too difficult to think of many different application areas where you can imagine it would be reasonable to model a response or a mean response as a monotone function of one or more covariates. So certainly in economics, it's very standard to assume monotonicity for utility functions and things like that. I think in a lot of biomedical applications, genetic examples, these are very reasonable assumptions. So I'm going to be interested in the multidimensional setting, so where we've got several different covariates. Actually, this has been studied quite a lot in the genetics literature, where, as I say, there are lots of cases where you might think that phenotypes are monotone functions of covariates. If you have many different covariates, it's kind of desirable to try to think of some simplifying structure, the simplest of which would be an additive structure, but several others of which have been also studied. But these have often been found to be too restrictive. And so in this talk, I want to think without assuming some additive or low-dimensional structure within the isotonic function, how can we try to estimate this? Okay, so if we are working with covariates on R to the D, then we have a natural partial ordering. I'm going to be thinking about the set of block increasing functions, so just increasing in each coordinate. And I'll write the class of block increasing functions as curly FD. And then our basic problem is, let's assume that we have independent observations, so covariate response pairs. Our covariate is xi and takes values in 0, 1 to the d. And our response yi is real valued. And I'll think of this simple regression model where we can write yi as f0 of xi plus some error epsilon I. And for simplicity, throughout this talk, I'll just think of my errors as being standard Gaussian, having a standard Gaussian distribution. That's an assumption that could certainly be weakened, but it's not really the main focus of this talk here. There are sort of two classes of problems here. One is where we might think of covariates as being fixed and the other as random. And there are different applications where each might make sense. let's say we were doing some sort of chemistry experiment and we wanted to look at the way in which a rate of reaction depended on the concentration of some catalyst that we were putting in to our experiment, then we would predetermine the concentrations of the catalysts that we were going to try to measure the rate of reaction at, and so it would be natural to think of those as fixed in advance. On the other hand, if you were a doctor and you were measuring, say, the heights and weights of patients who came into your surgery, then it would be more natural to think of the covariate as being random. So both fixed and design regression problems crop up in applications, and we're going to study both here to kind of preface what will happen later. The fixed design case is actually, from a technical point of view, somewhat easier to study. Okay, so I'm going to think about the simplest estimator you could possibly think of within this class, which is just the least squares estimator over the class of block increasing functions, over this class curly FD. So one thing that you'll notice immediately about this definition is that I'm only constraining the values of the estimator at the observed design points. So there's a sort of non-uniqueness in the way that I might extend this function to belong to the class curly FD. That's not really too much of an issue for us because actually the risk, the sense in which we're going to measure the loss here is in terms of its empirical risk, so we're only going to measure the loss at the observations. There are very natural ways you might think of the kind of, say, the smallest function that belongs to this argmin. Okay, here's one more observation that whether we're in the fixed design case or the random design case, our design points form a DAG, a directed acyclic graph, with respect to this natural partial ordering. I should perhaps have said that in the case of the fixed design, my focus is going to be on the case of a lattice. So this simple lattice like we have drawn here. But even in the random design, I can think of the partial ordering on the design points induced by the natural partial ordering induced by the design points and the DAG. Okay, so if we're going to think about feasible vectors within that satisfy all the monotonicity constraints that we require, we can think of them as lying in the monotone cone. So this is an intersection of half spaces, and I'll write that monotone cone as curly M of G. So I don't want to focus too much on computation in this talk, but just to mention that this least squares estimator is computable. So you can use something like Dijkstras algorithm. So if let's say I've got two different half spaces. Maybe I'll draw this with a different color. So if I want to project onto the intersection of these different half spaces, I can think about the polar cone that looks like this. And the most naive algorithm, which would be sort of von Neumann's algorithm, would say, if I start with a point here, then I would project onto one and then project onto the other. But what you immediately see is that that's projected onto the wrong point. Right? This was the closest point within the intersection, and my algorithm would sort of terminate here because I belong to the intersection, but I'm not at the closest point. There's an alternative called Dijkstras algorithm, which allows you to, you project, and then you come back like this, and then you reproject And the kind of memory means that you do indeed converge to this optimum here. Or you can use interior point methods as well. Okay, so there has been a lot of work on the basic isotonic regression problem, but almost all of it has been confined to the univariate design setting. So this is a problem that goes back more than 60 years now. But then there have been several results on rates of convergence, and more recently on oracle inequalities. And I'll say more about that later on in the talk. There's another recent paper by Chatterjee, Gundabuyina, and Sen that looks at the bivariate case for the fixed lattice design. And then there are other sorts of results that do work within sort of these simplifying structures, and the simplest of which would be to assume you've got an additive model for your regression function. But that's a sort of separate line of work to the direction we're going in this talk. Okay, so let's focus on the case of a fixed lattice design, and let's suppose that our covariates take values on this grid. And so I'll think of, just for simplicity again, I'll think of my sample size as being a dth power of an integer, and I'll say it's a dth power of n1. Okay, well in that case I can think of my sort of true signal vector as being theta 0, and my estimator as being theta n hat. That's just the least squares estimator at the observed design points. And then my risk function I can think of as being a function of theta n hat and theta 0 rather than fn hat and f0, and it's just going to be the average squared error that I make on the design points. Okay, so if I want to compute the least squares estimator, I have to think about projecting my response vector y1 up to yn onto this monotone cone, this intersection of half spaces. And there's a very beautiful recent result due to Saurav Chatterjee. So there are two different S Chatterjees involved in this work. There's my collaborator, Sabyasachi Chatterjee, but this is a different one. This is Saurav Chatterjee, who's at Stanford. And so this is his characterization of the least squares projection onto a convex set. And here's what the result says. I think it's a very beautiful result. Let's suppose that mu belongs to a closed convex set K, and that epsilon is our error vector. So essentially it says that the risk of the projection of my observation onto the convex cone is characterized by this quantity T0, where T0 is the maximizer of this this expression here. So this is like the supremum of a Gaussian process. This isn't working very well. I wonder if this will work better. Okay. Right. A smart screen that's not so smart. Yeah, so we're looking for the maximizer as sort of expected supremum of some Gaussian process, and then we're subtracting this quadratic term. So if you think about this quantity here as a function of t, let's say mu is in the interior of my convex set, then because of the way that this sort of bilinearity of the Euclidean inner product, this is going to increase linearly in t to start with, and then you're sort of penalizing it with this quadratic term. So it's 0 when t is 0, but then because of the linear thing, it's going to be increasing to start with, but then eventually this quadratic term is going to win the race, and it's going to come down. And actually what you can show is that this is a strictly concave function that tends to minus infinity. Okay? But if we can locate the maximizer of this function as a function of t, and if this maximizer is greater than or equal to 1, then the risk of my least squares projection onto this closed convex set is essentially given by so if I'm looking at a squared error, then it's given by the square of t0. up to some error term that I can quantify. I think it's a very attractive result. It's very unusual to get also lower bounds on risks. So it's really nice to see that we're not losing anything here. Okay. So here's a picture to have in mind. And what is sort of obvious from the picture is that if I can find any upper bound T star for where I'm crossing the x-axis here, then certainly that's going to be an upper bound on T0. Okay? So if I want to bound the risk, then I can say it would be less than or equal to T star over n for any point T star, which is beyond the point where that function crosses the x-axis. Okay? So my strategy is going to be to try to find an upper bound for this point here, and therefore to bound the risk. Okay, so let's suppose that I fix some vector that belongs to the monotone cone, and then my notation here is just saying that every component of theta 0 in absolute value is bounded above by 1. So it belongs to the L infinity ball of radius 1. Let me write theta 0 bar for the constant vector with each entry equal to the average value of the signal over the entire lattice. And then I'm going to try to rewrite the left-hand side of this guy. So I'm going to bound this left-hand side above, and then if I can find anything that satisfies that inequality, any T star that satisfies that inequality with an increased value of the left-hand side, then I'm still okay. So let's bound the left-hand side above. I'm going to decompose this in a very obvious way by just subtracting and adding the theta 0 bar. But then I notice that this term doesn't have any dependence on theta, so I can pull it out of the supremum. And moreover, the expectation of this term is 0, because the expectation of epsilon is 0. Okay? So I can forget about that term. And then I can say, well, if theta minus theta 0 is less than or equal to T star, then theta minus theta 0 bar is not that much larger, because I know that theta 0 belongs to this L infinity ball of radius 1. So I just have to increase this radius by n to the half, and then I can rewrite this as a theta minus theta 0 bar. Sorry. And then the crucial point here is that this set is closed under subtraction or addition of a constant vector. So I can just translate this and talk about, now this is saying I'm working within the L2 ball, centered at 0 and of radius T star plus n to the 1/2. Okay, so that's just the fact that the class of monotone functions is closed under addition of a constant. Okay, so we've got this sort of Gaussian process here, and then this is linear in this argument here, so I can pull that guy out of the front and work within a ball of radius 1. And then I could just use Cauchy-Schwarz to bound this sort of first moment by a second moment to the power of a half, where the second moment's got a special name, and it's called the statistical dimension of the monotone cone. Who's come across the idea of a statistical dimension before? So this is a quantity that turns out to be very important in these sorts of problems, has many different equivalent definitions. There's a very nice paper that I'll mention several times, I think, due to Amelunxen et al. From a few years ago, called Living on the Edge, that presents a lot of properties of statistical dimension and illustrates its power in these types of problems. Anyway, so once I put all this together and I compare this with what I had on the previous slide, I just solve for T star. I've got to solve a quadratic equation, and I can see the way in which now the rate is driven by the statistical dimension of this monotone cone. Okay? Okay, so what's known about the statistical dimension of the monotone cone? There's a very nice result in one dimension that's again in this Amlungsen paper, that the statistical dimension of the monotone cone in one dimension is exactly equal to the sum of the first n terms of the harmonic series. So it's basically log n. And then in the bivariate case, it's also known that it behaves polylogarithmically in n. But in higher dimensions, nothing was known about this. And the key idea is to sort of inductively reduce dimension one at a time. So what you can imagine doing is you can take your lattice and you can divide it into slices, and then you can imagine removing the constraints that are between the slices. Okay, so that's removing constraints. It's enlarging the statistical dimension of the monotone cone. And then I can use basic properties of statistical dimension to say that I just have to add up the statistical dimensions of the corresponding lattices. And because I've got n to the 1 over d of these different slices, then each time I reduce dimension by 1, I have to inflate the statistical dimension by a factor of n to the 1 over d. So I keep going down, but I should stop at 2. I shouldn't go all the way down to 1, because I know that the statistical dimension behaves polylogarithmically in n when d is 2. I don't want to incur another penalty of n to the 1 over d by going down to d is 1 here. And this is something that we know how to control once we've got down to d is 2 using Dudley's entropy integral. And so we have the following result, that the statistical dimension of the monotone cone in d dimensions, of the cubic lattice in d dimensions, I should say, is essentially n to the 1 minus 2 over d. So the squiggles on the bottom here are disguising universal constants. And I'm also not going to worry too much in this talk about polylogarithmic factors here. So I'm really thinking of this as being basically n to the 1 minus 2 over d. So, okay, that means that we can just plug that back into this formula and get a bound on the risk of the least squares estimator. And here's what we find, is that for every d greater than or equal to 2, we can find a universal constant for which the risk of the estimator is bounded above by n to the minus 1 over d up to polylogarithmic factors. Okay. And moreover, you can't beat this result in a certain sense. So if you forget about the polylogarithmic factors, then here's a minimax lower bound. Who's familiar with minimax lower bounds? So here I'm taking, it's the same sort of supremum, but here's an infimum over all estimators. So here I was looking at the risk of a particular estimator, the least squares estimator, and here this is saying the best any estimator could do, if I take an infimum over all estimators here, is not much better. It's a lower bound, of course, so it's got to be smaller than this one, and it gets rid of the logarithmic factor. But other than that, we've got the same bound there. Okay, so to a statistician, that's sort of solving the problem. Okay, so yeah, maybe I should say something about how you come about this lower bound. The idea, this is a kind of key idea perhaps of our work, is that this lattice has a large antichain. So a chain is a set of mutually comparable vertices in this ordering. An antichain is a set of mutually incomparable vertices. Okay? And the point is that this lattice does have a large antichain that's illustrated here. It's basically all these points on the anti-diagonal of my lattice. So you'll notice that, let's say, if I take 2 points that are at the same level, vertical level, I can't compare these points because one is larger in the x direction and the other is larger in the y direction. And similarly, for any pair of points here, it's not too difficult to see that they're not ordered within this monotone cone. So what that means is that you can construct a lot of different binary vectors within this monotone cone. They could say each be 1 above this diagonal, each be 0 below the diagonal, so they look very similar on a large set, but you've still got this large antichain, and you've got complete freedom to choose whatever values you like for the signal on that antichain. And that sort of puts you in a good position to use one of the kind of standard techniques for coming up with minimax lower bounds, which would be Assuad's lemma. Okay. So there's a very interesting and I think very surprising overall picture here. So these results in 1 and 2 dimensions were already known. And those, perhaps you could say, were the sort of expected rates. So the basic idea is that a monotone function is differentiable almost everywhere, and therefore you should expect to get the same, I mean, the sort of intuition here is that you should expect to get the same rates of convergence as if you had one bounded derivative. Okay, so it's like having Hilda smoothness 1. And that would give you a rate in general of n to the minus 2 over d plus 2. But what we're finding is that in higher dimensions, you actually get a slower rate than would be predicted by that. You get an n to the minus 1 over d. And it's caused by these two sort of competing factors, one of which you can think of as being the length of the longest chain, which is basically related to the sort of smoothness properties of bounded Lipschitz functions or bounded Hilda 1 functions. And then on the other hand, you've got the large antichain. So in 1 dimension, it's this guy that dominates. In 2 dimensions, they actually turn out to have the same contribution, both giving this rate of n to the minus a half. But in the higher dimensions, it's the antichain that is the more constraining factor and that leads to the slower rates of convergence. So this theta tilde, that's hiding the logarithmic factors here. And the other particularly surprising thing about this result, which I think for people who know a bit about empirical processes has come as a really big surprise, is that we're seeing that a global empirical risk minimization procedure here, just ordinary least squares, can be minimax optimal, at least up to polylogarithmic factors, even over classes where the entropy integral diverges at some sort of rapid rate. So there are some negative results in a very well-known paper due to Birger and Massart from over 20 years ago now, where they show that if you're just looking over Hilda classes, that a global empirical risk minimizer cannot attain the minimax optimal rate once the entropy of your class grows like this, which means that when you try to integrate the square root of that, it's diverging. And so people have kind of taken those results and inferred that you shouldn't use, I mean, that's really a counterexample in some sense, but people have generalized that and come to the conclusion that you shouldn't use global empirical risk minimizers as soon as the entropy integral diverges at this rate. Are people familiar with entropy integrals? Yeah. But what we're seeing here is an example where, even though this entropy integral does diverge rapidly, we are still attaining the minimax optimal rate up to polylogarithmic factors. So I think that's the first example where that's been seen, and I think it'll be very interesting to see to what extent this is sort of typical behavior, and to what extent this is really, there's really something exceptional going on here. And I think for theoreticians, there's something really to try to get one's teeth into here. Okay, so I've talked about worst case bounds so far. And now I want to come on to talk a bit about adaptation. So very often in statistics, we're first of all interested in worst case bounds, sort of minimax rates of convergence. But often within parameter spaces, there may be smaller subparameter spaces of functions that have particularly simple structure. And so the simple structure I'm thinking of within the class of monotone functions is the class of functions that can be written as, where the signal is sort of constant on a relatively small number of hyperrectangles. Okay? So the simplest possible case would be where your regression function is itself constant. Now, that I think of as being a signal of particularly simple structure, because if you told me in advance that the signal were constant, more generally, if you told me it was piecewise constant with only a relatively small number of constant pieces, then I could estimate differently. I mean, in the simplest case, where it's constant, I would just use the sample mean of my observations to estimate the piecewise constant, the constant signal. And then I would know what rate I could get, right? On the squared error scale, I'd get a rate of n to the minus 1. And the question is, can the method where I'm looking at least squares estimation over this much larger class, I'm agnostic to the potential for the signal to lie within a smaller class, but is it possible that I can do nearly as well as if you told me in advance that I was in the smaller class? Okay, that's the sort of philosophy behind adaptation. And here is a result of this sort of form. So I'll write curly mk for the collection of signal vectors within my monotone cone, for which I can partition my lattice into hyperrectangles, k hyperrectangles, and the signal is constant on each hyperrectangle. So here's a result that I call it a sharp oracle inequality, and I'll explain that in just a moment. But it says that I can bound the risk above by the infimum over all k, and the infimum over thetas within this class are a sum of two terms, which I can sort of think of as an approximation error term and an estimation error term. Here's my approximation error term, and here's my estimation error term. So the simplest possible case here would be, let's say that the true theta 0 is constant. That means that k is 1 here. This term I could then think of as vanishing, and I'm getting an adaptation rate of n to the minus 2 over d instead of n to the minus 1 over d, again ignoring the logarithmic factors. So I'm getting a faster rate of convergence than I would have had over the larger class. And I can see the way that this increases with k. So provided k is relatively small, I'm doing better than the worst case rate. It's called a sharp oracle inequality because the leading constant in front of this approximation error term is 1. There's no kind of universal constant in that term. And writing in this way, I mean, you see, for instance, let's suppose that I could write it my signal as piecewise constant on k pieces, but it was very close to being piecewise constant on k minus 1 pieces. So there was only a very small difference between the signal levels. Then actually, this term might be smaller than the additional contribution I get from the reduction I get by thinking of this with a k minus 1. So I can take the infimum over all things here, which is kind of nice. The way that these two terms trade off against each other. Any questions about that result? Okay, and here's a sort of a lower bound. It's a different form of lower bound from what we saw before. This is not a minimax lower bound. I'm not taking an infimum over all estimators here. I'm just looking at this particular estimator, the least squares estimator, and I see that essentially this rate that I'm getting from this term here can't be improved. So even in the constant signal case, where the true theta naught is 0, when d is 2, the lower bound is n to the minus 1, and actually it's kind of nice that I've got logarithmic factors here. That's sort of improving the lower bound. I'm getting a larger lower bound. Some logarithmic penalty is necessary. And when d is greater than or equal to 3, it's n to the minus 2 over d, which is matching. So in the case where k equals 1, that's matching the rate that's being given by this term here. So again, if we're to look at these results, when we're in the low dimensional case where d is less than or equal to 2, I can adapt at parametric rate up to polylogarithmic factors in 1 and 2 dimensions. So I'm doing almost as well as if you actually told me that the rate was piecewise, the signal was piecewise constant, even though I didn't know that at all. The estimator didn't know that at all. In the high dimensions, I do get faster rates than I had in the worst case, but I'm not getting the parametric rate. Okay? These are slower rates. This is a sort of strictly non-parametric rate of adaptation here. So we are getting the minimax rate over the large class, but we're not getting the minimax rate over the small class. So it would be an open question as to whether there were another estimator, for instance, that could simultaneously attain these optimal rates over both the large class and the small class. Any questions?
So, when in the previous thing you have this approximation by piecewise constant over rectangle, what type of smoothness property govern the decay with k of this? If you want, I don't know, if you ask what rate you receive from this, if theta has a certain amount of smoothness. If theta has a certain amount of smoothness, like mixed Holder smoothness or something, you might be able to say something about this approximation term. And how to balance.
So I'm not making any assumptions about the smoothness of the signal, only that it's...
Yes, but now you have an approximation term.
I do have an approximation term, yes.
So if the signal happens to have a certain smoothness, you might be able to say something about...
Yes. So I should think of monotone functions as being a little bit like bounded Lipschitz functions. So it's sort of Holder 1 smoothness in the one-dimensional case anyway.
Really? The monotone function can have jumps.
That's right, but they're nevertheless differentiable almost everywhere. And if you were to look at the entropy of the classes in say, in one dimension, it would be the same as if you have Holder 1 smoothness.
In addition to being monotone, you have something about the derivative or something intermediate. Or can you infer something?
If you have less than or equal to 1 smoothness, that doesn't help you. If you have more than 1 smoothness, then it's the smoothness itself that would drive things, and the monotonicity wouldn't help you. Okay, so now let me say something about random design. So I'm going to think about the case where my design distribution is uniform on 0, 1 to the d. I can weaken this assumption somewhat if the design distribution has a density with respect to Lebesgue measure that's bounded below by a positive constant and bounded above by a positive constant, I could get very similar sorts of results, but let me just focus for simplicity on the case of the uniform distribution. And now my risk function I do need to think of as being a function of fn hat and f0, and I can write that as an expectation of the L2pn squared loss, where pn here is the empirical distribution of the design points. There's a typo here, this should be an n. Okay, so essentially the results are very similar in form to what we had in the fixed design case. We again see a worst case rate of order n to minus 1 over d. The logarithmic exponents are a bit different, they're a bit worse in the random design case than the fixed design case. And we also get a sharp oracle inequality of a similar sort of form to what we had before in the fixed design case. But even though the results look very similar, I have to say that the proofs are significantly more challenging in the random design case. So to give some sense of this, if you look at the class of monotone functions, you have an L infinity truncation as well. Then the regular entropy is of order epsilon to minus 2 into d minus 1. And so if you were to use a standard chaining argument, you would get a suboptimal rate of n to the minus 1 over 2 into d minus 1 for the risk. As I explained in the fixed design case, what we were able to do is to decompose each of the lattice into slices and then think about removing the joins between those slices. We don't have that sort of regular structure in the random design case, and that's part of what makes things significantly more challenging. A very basic sketch is to start by looking at the adaptation risk when f0 is 0. And you can approximate the L2pn squared norm of fn hat by the L2p norm over the when you've got an L infinity truncation. As always, in some sense, with least squares problems, you're going to start from a basic inequality. You say that your risk, which I can write like this, of your estimator fn hat, or at least the loss is smaller than the loss at the truth, which gives me the epsilon squared there. And if I rearrange that, it tells me a way of bounding this p of fn squared, which is the same as this guy here, which is what appears in here. And then, so I can see that basically to control this guy, I want to control this one and this term, and this is, so gn, this is just the empirical process, it's root n times this one over here. And really, if you can control this one, then you're done, because that's essentially the same argument. So we've reduced things to trying to think about controlling this type of empirical process here. And here is the game. We're again going to divide things into slices. And even though we don't have a kind of fixed design where we know exactly how many joins we're removing and things, with high probability we know how many data points lie within each slice, and we can therefore control with high probability the size of the largest antichain. And moreover, we've got control of the how big the envelope function for the class can be within each slice, and that decays, because I know I'm working with a class of decreasing functions, that decays in L by a power of L to the minus a half. So that's just a very sort of quick sketch of how we prove things. And then the corresponding sorts of results here that we again have a minimax lower bound over the class and a lower bound on the risk of the least squares estimator at 0, just sort of paralleling what we had in the fixed design case. There's something kind of interesting here. Let's say you're in the d equals 2 case, and you want to think about the largest antichain that you have. So I can think of one coordinate as being ordered, and then the size of the largest antichain would be, say, the size of the length of the longest decreasing subsequence within a uniform permutation of 1 up to n. Okay, so this is something that probabilists have studied an awful lot. And there's a very nice result called the Adage-Zekeri's theorem. And it says if you have a sequence of length r minus 1 times s minus 1, and you add 1 to it, then within that sequence there must be an increasing subsequence of length r or a decreasing subsequence of length s. Okay, I think there's been a lot of work done by probabilists on length of longest increasing or decreasing subsequences of uniform permutations. So we were able to borrow some of that theory here. Okay, so let me wrap up and say that isotonic regression behaves rather differently when, well, you could say D is 1 and D is greater than or equal to 3, and D is 2 is a sort of transitional case here. We have a worst case rate and an adaptive rate in the fixed design case, and similar behavior in the random design case. I think there are still lots of open problems. So how can you study isotonic regression on a general DAG? So let's say where you have fixed but non-lattice design. Can you deal with other global loss functions, particularly in the random design setting? What can you say about pointwise rates of convergence? So how well you're doing at a particular point rather than globally. What can you say about other shape constraints in general dimensions? I think it's particularly interesting to ask, are there other settings in which empirical risk minimizers can attain minimax optimal rates, even when entropy integrals diverge? Okay, so the paper has now been on the archive for about 3 or 4 months, and this is the main paper on which that work's based. Thank you very much for your attention.